Okay. It's yours. Yeah, thank you very much, and very good afternoon, everybody, ladies and gentlemen. It's a great pleasure to welcome you here to this press talk. Professor Forytta has already mentioned the reason behind it. We are running our biannual ISAM conference, which is the International Symposium on Additive Manufacturing. Additive manufacturing is one of these technologies that we nowadays call disruptive technologies. So we are expecting additive to change the world of manufacturing on the one hand, but also change the quality, the performance of products that can be made by additive manufacturing per se. So as a short introduction, additive manufacturing is a layer-by-layer technology by which you can build up 3D structures, 3D parts. And the major question that people involved, in particular people from industry involved in additive manufacturing today, is how can this disruptive technology be brought to real life, into industrial application. So this is one of the reasons why a couple of years back we at Fraunhofer IWS, in collaboration with the Technical University of Dresden, thought about implementing or starting this type of a conference, which has now matured to a conference where we have about 300 participants coming from literally all over the world. We have presentations which are invited presentations only, so we are gathering the experts in the field of additive manufacturing here in Dresden. We have 5 keynote speakers, and Professor Burrell from the US is one of the keynote speakers, and we are happy to have him here on the board this afternoon. Now, the subtitle of ISAM 2019 is tackling the materials and processing challenges, and from that you can conclude what are the major issues that the community is talking about. It's on the one hand materials, how to find the right material that can be processed, that gives the right material or properties for the components, and how to find the right additive manufacturing process to make the component, the part, in an economically feasible, productive, and also high quality way. Now, the ISAM does not only include plenty of talks, high-level presentations from experts from all over the world. We also have an elevator pitch contest where within 3 minutes experts are asked to present their topics, and we have a best poster contest. So we also have contributed papers in addition to these invited papers. Now, before I stop and hand over to Professor Brückner, let me ask a question and give the answer. Why Dresden for ISAM? What is the reason why we have this conference in Dresden? Well, the answer is pretty simple. It's a manifold answer, but it's pretty simple. Dresden is one of the AM hotspots areas in Europe. And Fraunhofer IWS is proud to be one of the leading institutions doing research and development on additive manufacturing in the world. We have a very strong collaboration with the Technical University, with TU Dresden, and being a professor and a professor at the university and the director of this Fraunhofer Institute, myself, I'm kind of a blueprint for this collaboration between the university and Fraunhofer. We also have a very strong collaboration with industry. So our mission basically is to help industry to innovate, to find new products, new applications. And with that, we are coordinating major or large-scale programs and projects. Forytta has already mentioned Agent 3D, which is a 45 million euro funding plus 45 million euro industry contribution project. And there are also projects such as Future AM, which is a Fraunhofer internal program that we are running here. So as you see, we are a real hotspot in additive, and this is the reason why we are coordinating and organizing this conference here. With that, I'd like to hand over to Professor Brück.
Thank you. Nice. So my name is Fraunhofer. I'm responsible for the Additive Manufacturing Center here in Dresden at the Fraunhofer IWS. And as already mentioned from Professor Leyens, so additive manufacturing has a quite significant role in Dresden. So they're together with IWS, other institutes, for example the IKTS, where we can focus with various technologies on really various branches in additive manufacturing. So mainly dealing with branches like aerospace applications. We will hear later on from Laurent Pambaguian about the space applications. We're dealing with medical technology, with production engineering, with tooling, as well as also with applications coming from the automotive. Yeah? So quite various fields of applications, and since about the 90s we're working on such applications, and nowadays we extended these capabilities, extended laboratories, and so we raised the AMCD together with the Technical University of Dresden. And as you can see outside, we're still extending our laboratory space to even increase new modern technologies. Yeah? So with these relevant AM technologies, we are able to not only look on the process itself, it's also feasible to actually have a look on the whole process chain, including pre as well as post-processing regimes. It means how to actually prepare a part, have a look for the right materials in the beginning, and finally we can also have a look for the heat treatment, to the post-machining effort, and so on. So we have a look for the whole process chain, and this is actually our aim, because we see this as a, let's say, way to come to a real additive manufacturing part. So major aspects for us are the also development of system technology, which means that we develop nozzle systems, some tools for digitalization, Industry 4.0. We're using these equipment to actually go for the right process with new materials, so also to increase the usable materials. It's a quite significant direction from us, and also to increase robustness as well as the flexibility. So which means in additive manufacturing we can shift from one geometry to the other, from one batch to the other. So we can directly load new CAD data and come from one design to the other, from one build job to the next one. As already mentioned from Professor Leyens, we work on quite big projects. So one is the Agents 3D, where we have various technology-oriented projects involved. So which means we're focusing on large tools, large parts, for example, for railway systems. But it goes also to be tiny structures, for example, for the dental industry, small brackets, small components which can actually reduce invasive surgery for such medical or dental applications. But other projects, for example, so-called multi-beam is focusing on the right material on the right location, which means we can actually not only produce a part out of a single material, we can actually have several materials included in one component. So in really stress and loaded component areas, we can focus on quite high strain materials, and other locations which are less loaded, they can actually be manufactured by more cheap materials. And we're also happy to work with ISAM, for example with the Athena Space mission, a really big optical bench in diameter of 3 meters, so a really big part which will be manufactured here in-house, and Laurent will give you some more explanations about this later on. So just a summary about the AMCD in Dresden, and I would like to hand over to Stephanie Brickwede.
Thank you so much. Thank you for having me. My name is Stephanie Brickwede, and I'm responsible for additive manufacturing within the corporate Deutsche Bahn, which is one of the biggest European railways. And we discovered additive manufacturing nearly 3 years ago. And what we do is we reprint spare parts we can't get at the markets anymore. So we focus a lot on obsolescence management, and you might have experienced it yourself. So this also has a lot of influence also on our punctuality. We wait for spare parts up to 9 months, sometimes even longer. We can't get those spare parts for older trains or infrastructure anymore from the OEMs, from the former suppliers. And this is when we think about using additive manufacturing or 3D print the part. Most of those parts we've already printed. Those are more than 6,000 parts now. Already go with the infrastructure or being built into trains. And this is a huge variety. We talk about plastic parts, we also talk about metal parts. And as you might know, trains are usually big and heavy and not small from the size, and lightweight is not our first focus aim. So what we are looking for are big metal parts. And the good news is we're not alone. We've initiated a network which is called Mobility Goes Additive. And within this network we focus on different aspects of additive manufacturing, always from the user's perspective. And we've initiated a working group with 6 other European railways. And yeah, they all have to suffer from the same problems. So what we would need are big parts we can reproduce. And the needs of rail are a bit different to other sectors. So we can't just use the same materials. We have to focus on our needs, and we have a lot of norms we have to fulfill, of course. The certification process is a crucial one also within railways. And in the meantime, we've succeeded for different use cases. We're really happy about that. And those use cases come from trains, infrastructure. We've already built little signs for blinded people. So we also increase the comfort of the whole railway system by using additive manufacturing. And this is our main aim, and I'm really happy to be here to learn more about the latest technologies, because this is something you can't change anymore. Additive manufacturing is the development of this time, and there will be a lot of more use cases, and I would always like to encourage also small and mid-sized companies just get started. And yeah, if they want to know how, we can also give them some examples, because we don't own any machines. Yeah. Thank you so much, and yeah, maybe I can hand over now.
Okay, my name is David Burrell. I'm with the University of Texas at Austin, and I've been asked to say a little bit about the university, a little bit about my research, and then a little bit about materials in general for additive manufacturing. So first, the University of Texas. We tend to rank universities relative to other universities. The University of Texas at Austin is a large public university. We have 53,000 students at the university. The university overall, by world rankings, is typically in the 30 to 35 number list. The College of Engineering, where I work, is within the United States, ranked typically number 9 or number 10 within the United States, as is the Mechanical Engineering Department. Among public universities within the United States, we're ranked typically number 4 or number 5. Within additive manufacturing, the greatest fame is the invention of selective laser sintering, which is the first of the so-called powder bed fusion processes. Was invented in Texas in 1986 or so about 32 years ago. And I've been working primarily with powder bed processes since that time. The first materials patent that I'm aware of was in 1990, was one I was the lead on for materials for laser sintering, and we've continued to work in that area. The current research I'm doing now centers around issues of reliability and consistency of properties for polyamide materials, for plastic materials. Polyamide or nylon is a very popular material for use in additive manufacturing. According to the Wohler's report, which is one of the standard industrial reports, of the polymers used, feedstocks for additive manufacturing for polymers, about a third of the polymer feedstock in additive today is polyamide for powder bed fusion. And the problem is that the properties are often unpredictable. This is the reason, for example, why certification is so important, is for this reason. So what I've been working with is, most recently, is a way to look at the machine for doing additive manufacturing, to understand how the machine operates, and then based on that, to be able to predict where good parts can be built in the machine. And this is an important issue for consistency and reliability, and we're very happy with those results most recently. So, to move on to speak a little bit about where we are with materials and additive manufacturing. I tend to break materials into by process within additive manufacturing. According to ISO and ASTM, the standards development organizations, there are 7 main classes of additive manufacturing process. And within each of those classes, the materials requirements really are quite different. And this is not unique to additive manufacturing. This is the same for, if we look at, for example, machining processes or welding processes or forming processes, for example, or casting processes. Within those groups, the feedstocks must have specific properties or behavior in order to be successful. So not every material can be machined, and not every material can be cast, and not every material can be additive manufactured. So within those groups, within these 7 groups, there are a number of areas where only a certain class of materials can work. So for example, perhaps the easiest is the group called vat polymerization, which includes stereolithography and binder jetting. These areas, the material must be a thermoset polymer, it must be photosensitive in order to cross-link when the light hits the material. So if it's not a cross-link photopolymer thermoset, then it is very difficult to work with in these areas. For laser sintering, we like so-called semi-crystalline or crystalline thermoplastics, such as polyamide or PEEK, polyether ether ketone. These types of materials are the most popular, and the so-called amorphous polymers do not work so well. We switch to material extrusion, which is a very popular process, in part because the machines are inexpensive. In this case, the materials are amorphous thermoplastics, and the materials that work for powder bed fusion typically do not work very well for materials extrusion. Anyway, and so on. So one of the important issues that we've dealt with in the last 10 or 15 years is to make sure that the material really suits the process, as well as the working service properties of the part. These are the important areas. So with a little bit of time I have left, I'd like to say something about the directions in materials that I see. There are a number of areas that I think are exciting looking to the short-term future. One area is that we're developing for certain materials enough of a database to be able to reliably predict the working properties. And these properties are being gathered together into databases, for example, the Granta database in the United Kingdom. And this has a significant benefit for designers because the designer doesn't know the details of the process, whether it's additive manufacturing or, say, forging or casting, but they want to know reasonably well what the properties are so they can do design. And these databases will allow us to do that. The second area is, I think it's time to generate so-called manufacturability indexes for feedstocks. We have, for example, with machining, we have machinability indexes that are assigned to materials to say how easy or difficult it is to machine. The same for casting. We have castability or formability. I think it's time for an additive manufacturability index where we can look at a material and say quickly and easily and to communicate how easy or difficult it is to machine. I'm sorry, to manufacture using additive processes. I think the other, where we are headed with materials, there are a lot of companies that are forming materials. I think there are two areas in research, and I'll close with this. One area in materials research is people are being very inventive and explorative and trying new materials. I think, for example, there's a lot of work, a renaissance of work with ceramic materials, with high energy materials or glasses, and as well as a variety of metals. This is going on. But there also is a second group that's dealing with really trying to dig down deep to understand fully how some very traditional materials work, like titanium 6-4 and the molybdenum chromium alloys for metals, for example, to really understand this so that we can really get these into application areas. And I think with that, it's a good place to stop, so I'll pass on to the next speaker.
Last but not least. So thank you for inviting me to this roundtable or press conference. So I am Laurent. My boss would tell you that I am the guru of additive manufacturing at ISA. I prefer to call my name the dinosaur of additive manufacturing at ISA because I started the additive manufacturing back in 2004. At this time, there was one person convinced that additive manufacturing is a changing technology, a game-changing technology. It took some years to start, and then more and more people realized that indeed additive manufacturing is something that that will change the way we are conceiving spacecraft and plenty of other things. So how did we start that? Perhaps at first I come with what is ISA. So ISA, let's say NASA is the equivalent in the US of ISA in Europe. It's one of these very few space agencies that are dealing with all the different aspects of space, meaning science, Earth observation, telecommunication, navigation, exploration, human spaceflight, launchers, and the directorate to which I belong is technology development. We have a budget that is a bit more than 5 billion euro per year, and we distribute a very, very large amount of this budget back to industry for developing satellite and technologies. Now, I can say how we started with additive manufacturing back in 2004. And I think that around the table, everybody started the same. We started by making mistakes, thinking that it's a very cool technology. We can place material where we wish instead of removing material from a big block. But at the starting point, we were not, well, I was not thinking about what does it mean. It means that you have to change totally the design rules, that you stop having 90-degree angles that you see everywhere. You have the possibility then to adapt your design to, on the one hand, the function of the part that you want to manufacture, and also the load path that will go through this part, and also the manufacturing of the part. It took us quite some time to evolve into this understanding about what is additive manufacturing with respect to providing the right function to the part, and to see the design freedom that additive manufacturing can bring. In fact, it does not give design freedom, it gives different rules. It gives other constraints and a lot of freedom in terms of shape that we can make, indeed. And slowly, the European Space Agency has been taking the lead with respect to additive manufacturing for space in Europe. And back in 2014, we initiated the so-called harmonization program, where we tried to look at all the aspects that are important for putting into the next generation of satellite additively manufactured parts. And for that, at the end, we came with a roadmap where we are looking, as Frank was just saying, to the holistic approach, to the end-to-end manufacturing. So we are looking at what are the rules for design and how the design can be improved. We are looking at the raw material and what is the quality of the raw material that we need for additive manufacturing, how it can be recycled, what are the new materials that need to be developed specifically for this process. We are looking at the way we are processing the material inside the machine and what are the different rules with respect to processing depending on the process that we are using. We are looking also at all the post-processing, meaning that we need to have heat treatment, we need to have surface finishing, we have the need to get machining of the part, etc., etc. We need also to look then at the quality insurance. How can we be sure that there is no critical defect in our part and that our part will not break? Perhaps just a parenthesis with respect to this. In our business, it is prohibited to have a part that breaks because a satellite cost is several hundred millions and we cannot afford to lose one part because we have not been qualifying properly one part made by additive manufacturing. So quality insurance, qualification is also something that is challenging because we qualify with 1, 2, 3 parts and it's a lot of we need really to ensure that our validation of the part is thorough. And we are dealing for the last years now, for 2 years, we are dealing with standardization because if we want to get parts on board of the satellite or on board of the launchers, we need to have rules, in fact, for acceptability of the part. And rules also for finding how we have to process the material to get an acceptable part at the end. And perhaps the last word is about where do we go with additive manufacturing. We go in plenty of different directions. We go in very small, we go in very big, we go in ceramics, in metals, in polymers, in composites, in regolith. We start looking at can we print food for the astronauts. We start looking at can we have telemedicine if we have a long-term exploration mission. So we are extremely open with respect to the application of additive manufacturing. And additive manufacturing has triggered some years ago a broader initiative from the agency that is called advanced manufacturing because we discovered with additive manufacturing the number of new possibilities that we have to prepare the next mission for ISAM. But additive manufacturing is one among the different technologies that are enabling and that are coming now with a good maturation. And so we are speaking more and more about advanced manufacturing, for which additive manufacturing is a large part, but we are also speaking about solid state welding, we are speaking about advanced composite manufacturing, advanced non-destructive investigation, software for modeling, etc., etc. And I think I can stop.
Well, thank you very much, everyone, for the insights you shared with us. I think it's time to hand over to our colleagues from the press. If there are any questions, because there was a lot of information to digest, maybe we can just start by actually asking the first question. Is there anyone here with us having a question? Just show of hands. There you go, Mr. Böhler.
You're talking a lot about additive manufacturing, but I miss one new technology or possible technologies, Internet of Things. The changes for the industry is clear all for you, so I think. But how can the possibilities of Internet of Things or the challenges there, or maybe of additive manufacturing, influence the other technologies? How they are connected? what happened on this issue of industry. I think that's the most challenge for all industries, for all branches, for everybody.
Maybe I can try to answer this question. I think I would, rather than calling it Internet of Things, I would call it Industry 4.0.
Yes,
if that's okay with you. That makes it, in my world, a little bit easier. So additive manufacturing is a real digital process, if you will. I mean, you're producing your part layer by layer. If you break it down, you could even speak of voxels, which are little parts of material that you lay down in a very controlled manner. What research and development is looking at these days is to have a fully digitalized processing chain that starts with a material. So what we need is eventually digital information about the material. Then have digital information about the process, and have digital information about the part that comes out of the process. And then the secret really is how to link these three in very rough manner described areas. So the data, the material, the process, and the part. How to link it in a meaningful way, and we call that the digital twin. So what we are working on is really to have a digital image of the real world, starting with the material, of the process, and the full component. And that then gives us really also the possibility to start with the component properties first, select the right process and the right material to have these component properties that are wanted. So this is, I mean, additive is really, since it's a highly digitized process, it's an ideal process for this type of research and development. So Industry 4.0 in a wider meaning definitely plays a major role, or additive plays a major role in Industry 4.0.
Is there an interdependent situation? What do you think?
Yes, as I said, I mean, we try, as engineers, we always try to understand how, for example, a process that makes the material and the part at the same time, and this is one of the special features of additive, actually, to make a component and the material at the same time in one step, if you will, how this influences the component properties. And Professor Borel, he pointed out that reliability of properties, I mean, quality, reliability of quality is one of the key issues. And so we try to understand the correlation between material process and materials properties or component properties. And that can be ideally be done by a digital twin imaging, basically, the real world in a digital way.
Did that answer your question?
No? Yes?
Is anyone here who would like to contribute something to comment this topic?
Yeah, perhaps. I fully concur. So, additive manufacturing is a material and process technology. It is a digital technology, and it is a system technology. So,
Three.
yeah,
Yes.
three aspects. At the agency, we have another so-called cross-cutting initiative, meaning that everybody dealing with technology is looking into this cross-cutting initiative and how can we make it, and it is named Design to Produce. So we have also all the aspects that are the digital twin that need to be taken into consideration, but also collaboration between human and robots, or how do we lay up a factory if we want to go to a large mega constellation of satellite. So there are a lot of things that need to be taken into consideration between the physical world and the virtual world that we are dealing with.
Thank you.
Okay, so open road again. Or is anyone here with us who would like to contribute? Okay, open road again. Next question.
One question to Mr. Pambaguian. What is your opinion about the quotation of the additive manufactured parts, metallic parts, by the ISAM?
The quotation.
How many parts you have in one aerospace?
Okay. Today, none of the ESA missions have flown with additively manufactured parts. It doesn't mean that there is no European satellite that flew with additive manufactured parts, but ESA is perhaps more conservative than the commercial market, and so we are lagging a bit behind with respect to implementing parts on a satellite. This will change very likely in 2019, so this year, because it will be the first launch of commercial satellite with private-public partnership, where we will have parts made by additive manufacturing. What we can say is additive manufacturing, you shall not use it. You have to use it when it is wise, because what we want to do is to have high performance manufacturing and high performance space hardware. So we have been running some studies, even if it were paper studies, showing that if you are thinking additive manufacturing from the very early phase of a space mission, you can go from saving nothing up to changing the launcher that you will use for your satellite. Meaning that instead of having Ariane 5 or Ariane 6, you can use a Vega. That is a very significant saving in terms of launch cost. Another point that is also interesting is that we go with, as we have a lot of possibilities, we go for multifunctions. Multifunction, it means that we can have a part that will be structural, that will have some thermal hardware on it, so we'll have the control of the temperature. That can be also an optical payload or radio frequency to transmit signal from Earth and to Earth. Problem is that we have to associate that with a risk. So if you have a part that fails when it has three functions, you have a risk that is associated. So we are working on all these kind of aspects that are, as I said, system aspects that are extremely important. And for the next years, we will have more and more parts. We'll see plenty of Ariane 6, and we'll have more and more on Ariane 6 because there will be a lot of evolution of Ariane 6. We will see on telecommunication satellite, Earth observation satellite. Science, we have some very interesting projects that are run today with IWS on enabling technology because we don't know how we'll make the part at the end. So it will evolve also very much.
Thank you very much.
Okay, further questions?
I'd like to make just a provocating statement, and I like an answer from all of the panelists. I just read it a half year ago, just before the Formnext, in a magazine, that AM will supersede traditional technologies like drilling, milling, and cutting. This is the statement. I will not say my opinion. And then also from my, I like to be interested, what is your wish from the automation suppliers? Yeah, when I think about controls of the AM machines today available and the hybrid machines, what do you wish there from the automation suppliers, and how do you see such hybrid machines where you can do drilling and at the same AM technologies like you can have on Puma, DMG Mori and so on? What is your opinion about those machines?
Okay, so who would like to take the lead? Professor Brückner.
Oh,
okay.
Oh, please, oh, please.
Okay, Professor Brückner, and afterwards Dr.
Oh, Ben?
This one.
I love going to conferences and meetings where business people and executives come because there really are two types. The first type of executive comes to these additive meetings because they're very excited about the potential. And the other type, they're deathly afraid that additive will put them out of business. So this is I
always
think,
the same.
Yeah, exactly. To address the latter, from my perspective, the additive manufacturer additive manufacturing will make inroads where it's in industry, where it's economically meaningful to do so. And the limitation, at least today, is such that the economic benefit really comes from relatively small production runs and relatively complicated geometries. But all of these tie back to the cost. So I think as the cost comes down, it's primarily the cost of the machines, and to a lesser degree, the cost of the feedstock is what I see. I'm very excited about the possibility of these low-cost machines producing parts that have reasonable service properties, because that will bring the cost, that will be a significant disruptive change in cost. You know, to have a machine that costs maybe $200 versus $200,000, for example, has a big impact on cost. So I'm looking forward to that reality. But I think certainly for the near term, my crystal ball says that the people that are doing the standard manufacturing, it's going to be a long time before additive is used to make large quantities of parts in a routine pedestrian way. So,
Okay.
Yeah, I can fully agree to Dave. At the moment, the additive manufacturing plays a quite small role in the whole production world. Yeah, so it's less than 1%. But I think we have a strong increase from year to year, and we see additive manufacturing as kind of an extension to current manufacturing routes. Yeah, so as I mentioned before, you can actually fabricate a component out of several materials. Yeah, you can actually fabricate quite complex designs. So you can actually fabricate parts which are not able to producible in another way. Yeah? So this is quite interesting. So we can see an extension of applications, and in addition, I think if we see the market, yeah, at the moment, a lot of people is just standing in front of the pool and doesn't jump in. So because it's also related to trust, yeah. So I think even if the parts might yield the right material properties and so on, I think people has to be convinced, yeah. So in some of the companies, manufacturing routes are established since decades of years, and this has to be, let's say, overcome. Yeah? So and maybe a last point on that is that we can see also a lot of applications coming from redesign, repair, yeah, instead of not only fabricating a complete part. Yeah. So the combination between subtractive machining or conventional machining is quite important in relation with additive manufacturing.
Okay, Professor Brückner would like to add a comment to that.
Yeah, let me maybe address the other two topics you asked for, automation and hybrid machines. Well, I think the first part on automation, I tried to answer that with the Industry 4.0 approach. So within that, automation, of course, plays a major role. I mean, interference with a machine by a human being, by changing powders, things like that, is kind of a process that you would like to avoid for larger size production, of course. So process automation plays a role. Process control, by the way, if you conclude that or include that in automation, is extremely important. So since you're fabricating your part layer by layer, you can observe the fabrication process layer by layer. And if, for example, you discover there might be a deviation from the ideal process, you might be able to kind of react. If your sensing system is sensitive enough and quick enough. So you might, for example, include a repair process while you build up a part, rather than testing it or checking it after the whole part is being built. You might look at it and look at it for flaws or failure during your build. That is one part of the answer. With regards to hybrid machines, I mean, you mentioned some of these machine types that are on the market. There are certainly applications for those machines. where, for example, you're building complex parts that require intermediate machining. So you build up a part and then the shape is so complex that you cannot get access to it afterwards when you build it completely. So this is one of the examples where these hybrid machines are very versatile. And of course for specialty parts, very small lot sizes, and parts that don't require very high productivity. These machines are well suited because, I mean, one thing is clear, in these hybrid machines, one process is always waiting for the other one, right? While you're adding material, you cannot mill it away at the same time. So if you have a hybrid process, one process is always waiting for the other one to be finished. But it gives you advantages in terms of accuracy of the part, machinability of complex shaped parts, and so on and so forth. So there is room for these machines as well. Yeah.
Okay. So the auditorium asked for the whole perspective. I don't know if Stephanie Brickman would like to add something from the Deutsche Bahn perspective.
Yes, I'm coming from a user's perspective, and we are not a train producing company, we are just a maintainer. But what is really interesting to me is my company used to be a startup 190 years ago in the industry 1.0. Now we have to jump over, from time to time, not always, but we have to jump over some steps to get into 4.0. And this is exactly the point we have to face when we discover those spare parts we want to reproduce. You won't find any 3D drawings. If you're lucky, you will find a 2D drawing. Yeah? So that means you need a lot of engineering competence to first get the 3D drawing to build a digital twin out of the other part. And this is what I find really interesting. So the perspective might be a bit different. But coming from this user's perspective, we see a huge potential, and what I found really interesting was a study published by the ING Bank, the Dutch bank, 1.5 years ago, and they say by the year 2040, 50% of all parts worldwide will be printable, no matter what. Yeah, so I think the potential is huge. We've already discovered a bit of that within Deutsche Bahn, but we still have quite a way to go.
Okay, so Laurent again.
So when I look at industry, they are looking at two different aspects that are in fact only one. Lead time and cost. Okay?
Yes.
The two are in fact cost.
Yes.
And additive manufacturing will not replace all the traditional manufacturing. It will be merged into all the possibilities for manufacturing, the different technologies will, at a point in time, use additive manufacturing when it makes sense, and use other manufacturing technologies when it makes sense as well. And when we speak about additive manufacturing, in fact, we need to speak about post-treatment, like, do I need a coating? It will never be done with additive manufacturing. Do I need a welding? That will not be done with an additive manufacturing technology. Or to have any kind of machining that will not be done with additive manufacturing either. So it will not replace, it will be merged with all the others.
Or supplement.
Or supplement, yeah.
So don't be afraid. I think that's you could really combine all the expressions here. So I think it's time for the next question. We're running up to 4 o'clock. So are there further questions for our speakers from the auditorium? Okay. Well, then I thank you very, very much for being here, for sharing your knowledge and your expertise. Thank you for being here and asking questions, contributing as well. There will be very interesting and dense days ahead of us concerning additive manufacturing. If there are any questions left that don't come up to your mind right now, then you're very much invited to call me or to write an email, and I will try to answer you or to provide the contact. I wish you very much very good rest of the day. Have a safe trip home when it's cold outside. Thank you very much.